So they would talk about Kosovo, and I think it was also Guatemala National Forest.
Sounds good.
Yeah, okay.
They did put posters up, right?
What? Somebody left posters here. That is
Okay.
what we found.
That's good.
But it should be really a lot of fun.
So I'll make some announcements, but maybe I'll wait since some people seem to be late, and maybe we'll just get started. So today I'm gonna talk to you about one of my favorite topics, which is matroids. I actually wasn't sure if I necessarily was going to cover this topic in this class. It's one of many topics that I could cover or not cover. But I saw from your project proposals that a lot of people seem to be interested in this stuff, and you know, I should give you a product that you like, right? And you know, so, and anyway, so I'm happy to talk about this stuff. So I think I'm gonna spend, today I'm gonna give you kind of a crash course in matroid theory, and then we'll talk about the Hopf algebra, or at least one Hopf algebra structure on matroids. Okay. So what is matroid theory about? Well, matroid theory, you can think of it in many different ways. But one way that I like to think about it is that matroid theory is kind of an abstract theory of independence. It's a combinatorial model for what independence looks like. Combinatorial model for independence in mathematics. So in mathematics, there are several different notions of independence, and many of them have a lot in common, and matroid theory is basically the combinatorial theory that encodes what the essence of those independence theories is, what they have in common, and how that helps us. Okay, so I'll make the definition. A matroid is a set E and a collection of subsets sorry, let me say a collection I of subsets of E and these subsets are going to be called independent sets. Let's see, one of these markers has to write independent sets. Okay, so I is some collection of sets such that you need to have some properties, okay? And the properties are the following. Two of them are kind of easy. So the first thing is that we're going to agree that the empty set is always independent. Okay? And then, So by the way, what should you have in mind while I'm writing this? Maybe the most important example of a matroid is just the matroid of linear independence. So you can think of E as a bunch of vectors, and I is going to consist of the subsets of those vectors that are linearly independent. Okay? And so the empty set should be independent if you have I is a subset of J, and J is independent, then I should be independent. Right? So subsets of independent sets are independent. And maybe the least trivial of these properties is that if you have two independent sets, I and J, and one is smaller than the other, so let's say that I is smaller than J, then you can find an element in the big set, let's call it J, it's in the big set and not in the small set, such that you can add it to the small set and still be independent. Okay? So if you have two independent sets, one is smaller, one is bigger, then you can make the smaller one a little bit bigger using one of the elements of the bigger one. Okay?
There's two different I's there, right? There's the kind of curly I and
Yeah, so the curly, like my curly I, I should really be careful and make it very curly so that you can tell it apart from the other ones. So the curly I is the collection of all independents, and then a capital I, maybe this is not the best notation, is it? But it's standard notation, so I think I should use it. Capital I is the set, and the kind of, I don't know what you call that, cursive I is the collection of independent sets. Okay, so a matroid is a family of independent sets satisfying some properties. Okay? The merit of this definition is justified by the examples. So, example 0. Okay? E is going to be the set A, B, C, D, E, F, and script I is going to be the following collection. So I know the empty set has to be there. I know, well, I'm going to say these guys are independent. For example, let's say that I want ABC to be independent. If I want that, then I have to make sure that AB is independent, AC is independent, and BC is independent, because they're subsets, right? But I'm also going to say that these guys are independent. Okay? And one thing that I should point out is that I'm being a little bit lazy with the notation, but if I wasn't, this would look really horrible, right? Because really every one of these things is a set, and if I was to be more careful, I would put brackets around it, but then it would be very hard to read. And so I just write it like this. Okay, so I claim this is a matroid, and that means that it satisfies these properties, and it would take a little while to check it, but I mean, in principle, it would be easy to check. It would just take a while, right? I don't know. Let's take a smaller set and a bigger set. So here's AD is a smaller set, and ACE is a bigger set. So what does the third axiom say? It says that I must be able to add one of these guys to this guy and stay independent. So A I cannot add because I already have it here. E I cannot add because ADE is not independent. But C I can add to this guy and get this guy, which is independent. So the third axiom is some kind of an enlargement axiom that lets you take smaller independent sets and make them bigger. Okay? So that's, I claim a matroid. Now, let's do some more interesting examples. Like I said, let's say that E is a set of vectors in a vector space, and I is a linearly independent, is the set of linearly independent subsets. Okay, and so I could do this for any vectors in any vector space over any field. But let's do it, for example, in R3. So let's say these are the coordinate axes. And let's say that this is vector A. This is vector B. No, sorry. So let's say that the unit vectors are A, B, and C. And let's say that, let's complete this parallelogram, and let's say that this vector is D. And then let's say that maybe this is E right here. And maybe F is right here. Okay? So what are the linearly independent sets here? Well, the empty set is independent. What about the sets of one vector? Well, any vector is independent by itself except for F, because F is the zero vector. Right? And so actually, it's these guys that are independent. What pairs are linearly independent? Well, if you have F, you cannot be linearly independent. And if you don't have F, then all of them are linearly independent except for the pair DE. So, and if you see what I did here, this is the list of all subsets of A, B, C, D, E that don't contain, that are not DE. So these are the linearly independent pairs. What about the linearly independent triples? Well, if you have a triple of linearly independent vectors in R3, then there are bases. And so really I'm asking you to find the bases of R3 that are part of this thing. How can you make a basis of R3? Well, you should make sure never to use F. Always use A, because if you didn't use A, then you would be stuck being two-dimensional. So you have to use A, like I did in all of these bases. And then once you've used A, you need to choose two vectors out of these guys and make sure that they span the plane. So you can use B and C, B and D, B and E, C and D, or C and E. But you cannot use D and E. Okay? And so these are precisely the bases that I get. Okay. And so probably when I wrote this down, this looked very random. But the way that I got it actually ahead of time, I prepared class, and I drew this configuration of vectors, and I made the list. And this is the list that I got. Okay? And I claim that no matter what vectors you start with, if you let I be the set of linearly independent subsets, then this is going to be a matroid. Okay? And this is actually an easy exercise in linear algebra. So the empty set is linearly independent, basically by definition. It's very clear that if you have a linearly independent set of vectors, then every subset of it is linearly independent. That's also obvious from the definition. This is the only one that's a little bit more less trivial. And this is called the Steinitz exchange axiom in linear algebra. So if you have two sets I and J, and the linearly independent, and I is less than J, then what happens? That you have some, imagine that I have two sets of vectors. One is I, one is J. They're both linearly independent. This guy is smaller than this guy. So the span of this guy is a vector space of dimension smaller than the span of this guy. Okay? And if I have a vector of a smaller dimension, a vector space of a smaller dimension, so I have a big vector space, and I have a subspace of smaller dimension and a subspace of bigger dimension, then clearly I can take one of the vectors from the bigger subspace and add it to the small subspace to increase the dimension. Okay? And you can write down a proof of this. This is precisely what's called the Steinitz. What did I say? Steinitz Steinitz exchange axiom. Yeah. I'm a little bit worried that I might be lying about the name of this. It's somebody's exchange axiom, and I think it's Steinitz. Yeah?
So if we can, if looking at linearly independent sets in some vector space gives us a matroid, does a finite matroid give us, can we take a finite matroid and understand it as linearly independent sets?
So
over some vector space?
So the question is, so let me say a proposition here, that this is always a matroid. And I basically just mumbled the proof. And Zach's question is, can you reverse this? In other words, if I give you a matroid, can I always find a vector configuration that kind of realizes geometrically? And this is a very important problem in matroid theory, and the answer is basically no. And the answer is no in many ways. So there's, I could talk about this for a long time, but the answer is no. That the class of matrices is much bigger than the class of matrices that arise from this in a very precise measure. Like this is a measure 0 set inside the set of all matrices. Okay. Different example. E is the set of, and maybe I should say that these guys are called linear matrices or representable matrices. Okay. Example 2, they're called graphical matrices and they come from a graph. Okay. So here E is going to be the set of edges of some graph. Let's say the graph is finite and it's not directed. Okay. And I is going to be the set of cycle-free sets of edges. Okay? So let me draw a picture that I hope looks familiar to you. If it doesn't look familiar to you, then you need to get to your homework already. Okay? So here's a graph. And let me label the edges like this. I think this is how I labeled them in the homework. What are the cycle-free sets of edges? Well, for example, you should always avoid F because F is a cycle already. And so F should never appear as in an independent set. The other thing that should not appear is D and E together. Right? You always have to choose either D or E. What's a maximal? Let me make a definition, actually. So a basis is going to be a maximal independent set. Okay, so a basis is a maximal independent set. Okay, and two easy observations about this is that they all have the same size. So all bases have the same size. Why is that? The reason is that if you had two bases and one was smaller than the other one, well, for this reason you can take the smaller one and enlarge it, and therefore it's not maximal. Okay? So all bases have the same size, and the set of bases determines the matrix. Okay? And that's because the bases are the maximal independent sets, and then all the other independent sets are just going to be the subsets of those guys. Okay? And so, for example, here, what is a basis? What is a maximal independent set? Well, you're just going to throw in as many edges as you can. So you know you can never throw in F. You know you should always throw in A because it doesn't form a cycle with anybody. So definitely throw in A. And then what can you do at this point? Well, choose any. You cannot choose 3 of these edges, right? Because if you choose 3 of them, you're going to form a triangle, or this cycle. So you choose any 2, but you shouldn't choose D and E at the same time. So you get ABC, ABD, ABE, ACD, ACE. And again, that's precisely that list that I made over there. Okay? And so proposition, this is a matroid also. Called the graphical matrix. And so one thing we're seeing is that my example 0 is a linear matroid, and my example 0 is also a graphical matroid. Yep.
Okay, so if it's not a matroid, is there something that generalizes? Like, is there something that matroid, something that belongs to a larger class of sets if it were not a matroid?
Sure. I mean, there are things. So the question is, if you're not a matroid, then what are you? And well, I mean, there's 100 different answers to that question. But I mean, there are other things related to matroids, but somehow the topic of today is matroids. So let's talk about the things that are matroids. But it's a good question. I mean, how do you tell that something is not a matroid? Okay, it's a good question. And again, and not only is it true that I could go on for a semester about this, I have gone on about matrices for a semester. So the first joint course with Colombia that I did was all about matroid theory. And if you're interested, a lot of the questions you're asking me are answered there, and I'm very happy to point you to the right places. Okay. For example, let me give you a nice proposition that is not too hard to prove, but it's not obvious either. It's an interesting proposition. Proposition: every graphical matroid is linear. So if you come from a graph, then I can cook up a set of vectors that also realizes you. That's a fun exercise. Example 3, algebraic matroids. So you might remember that there's also a notion of algebraic independence. And so E is some set of elements of a field extension of a field F, and I is going to consist of the subsets of E that are algebraically independent over the ground field. In other words, the ones that don't satisfy a polynomial equation with coefficients in the ground field. Okay? So let's do this. Let's say, for example, that we do this in the reals and the field extension x, y, z. Okay, this is not a field. Right? These are the polynomials in x, y, and z. And so to make it a field, I do this. Rational expressions in x, y, and z with real coefficients. And let's take some elements in this field extension, okay, like the following. So let's say that A is x plus y plus z, or I mean, let's put some fractions so that it actually looks like B is x plus y, C is x minus y, is xy, E is x squared, y squared, and F is okay. I have some maybe a little bit fancier. Let's throw the complex numbers in here also. Okay. So that's still a field extension of R because it still contains R. And let me say that F is I. Okay. I the number. I the square root of -1. Okay, so, well, I mean, you can probably guess what the matroid of this thing is going to be, because we're just going to go back to example 0. It's going to be the same thing. Okay. So, for example, I mean, you start seeing the patterns, right? So, for example, you know that F is kind of a useless vector here. It's a useless edge here. And somehow F should be useless here also. So why is F useless? I mean, by useless, I mean dependent. Well, because I satisfies a polynomial equation with real coefficients, which is I squared plus 1 equals 0. So I is actually algebraically dependent over the reals. Okay? But the variables x, y, and z are not dependent. They're independent of the reals. Okay? Now, in both of these examples, we saw that here A was linearly independent to everybody. Here A formed a cycle with nobody. Is that true here also? That is true, and the reason is that A is the only one that contains the variable z. Okay? And so you can't have a polynomial equation involving A that only has the reals because you're not going to be able to cancel that z. Okay? And then, for example, D and E were linearly dependent here. They formed a cycle here. Is it true that they're linearly dependent here? Well, yes, because D squared is equal to E. So these are algebraically dependent. For example, B, C, and D are also algebraically dependent. And that would be a nice exercise to give to your algebra students. What is a polynomial equation satisfied by B, C, and D? Can you see it? B squared minus C squared is 4 times D. Okay, so when all is said and done, proposition, this is a matroid. And when you do it for this example, you'll see that I get the same matroid. Okay. Well, let's do another example. Transversal matrix. So here, the setup is the following. This is about pairing up two groups of people, or people and schools, or whatever. Right? So let's start with a graph where maybe the graph is divided into men and women. Okay? So maybe we have 3 men. And maybe we have 6 women. And let's say that we're going to put an edge between 2 people if they're willing to get married, let's say. Okay. So I don't know, maybe, and let's give them names, but the names are just going to be numbers and letters. I don't know, maybe 1 and A are high school sweethearts, and they always they're only willing to marry each other. Maybe, I don't know, maybe 2 would also marry A, but A wouldn't marry 2, so we don't put that edge. But maybe it's like this. And maybe 3 is really desperate, and I didn't say it, but 3 will really marry anybody. It's San Francisco. I don't need to explain this. funny because I explain this sometimes and people get really confused, like, why is there an edge between two men? Anyway, F is 12 years old. F is not going to get married to anybody. Okay. And so this is some graph of preferences, let's say. Okay. So E is some, let's say, a set of women. And I is the sets of women that could get married. And I don't know, the usual setup here is no polygamy and no gay marriage, like in a lot of places. That's the usual setup for this model to work. It's not a political statement. Really, you want this graph to be bipartite. Okay, that's the setup for this model. But this edge is not going to hurt us, so we're going to keep it there. Sets that could get married. Okay. Sets of women that could get married, right? Because we're talking about subsets of this. Okay. Yeah.
If a pair of people are both going to get married, at least one of them must be married in a solution? Or can they?
No, it could be that no one gets married, or it could be that we want to get as many people married as possible. The sets that could possibly get married simultaneously. That could get married, let's say, could possibly get married simultaneously. Okay, and so you start seeing some features. For example, as usual, F. We're not going to call the 12-year-old useless, but F is not going to appear in any independent set, right? F cannot get married to anybody. A can always get married if A hasn't been married, because if A is not married yet, then that means that 1 is not married either, and we can always marry them if we want to. So A is kind of a free element that we could always add if we want to. Now, I think I wanted to do something a little bit different, actually. Yeah, no, sorry, I did this. I didn't draw what I meant to draw. I mean, that would give me some other matrix, but not the one that I want. Okay, so really what I meant is that I wanted maybe these two to be in direct competition for 3, so they cannot get married at the same time. And then maybe 2 will marry any of these. Okay, so right, so I cannot get D and E married at the same time because there's only one person that they could possibly get married to. And that's it. Okay? And so if you carry it out, you'll see that the set is again the same one. Okay?
Except that B and C should be the ones who are willing to marry either 2 or 3. Yeah. And D and E should only be willing to marry 3.
Sorry, say that again?
So right now, D and E could pair off with 2 and 3.
Oh, yeah. So
I think you want that arrangement, but with B and C, D and E swap. B and
so
C.
I should take this. Take this and do this. Is that what you're saying?
Yeah, and there should be an edge, and then you should delete the edge.
And this one shouldn't be here. Yeah. Thank you.
Then B and C can simultaneously be happening.
That's right. Now, so this is okay. So now it's correct. D and E are in direct competition for 3, and then B and C are not. Okay.
So it's like looking for some sort of optimal match or something.
So we haven't talked about optimizing anything yet, but it's a very good question. I mean, so far we're just talking about whether it's possible to match. Okay. And so, if you know the matroid, then you would know which subsets it is possible to match. Okay. But then naturally, the next question you want to ask is, okay, is there some kind of optimal matching? Let's say, for example, if there's some prize that you're going to get, like maybe you're the matchmaker of a town, and maybe this is a dating service, and maybe it's a dating service where, because there's so many more women than men, maybe it's the women that pay, and so maybe the women have to subscribe and pay a certain amount, right? And the reason I set it up like this is because the ground set is the women, okay? But let's say really that each one of the women pays a certain price for getting married. And then you could ask, the matchmaker could ask, okay, what's the arrangement where I'm going to get the most money out of this? Okay, it's a very natural question, and it's just, I mean, people make a living out of these things, right? You're well aware of this. I mean, it seems that nowadays the way that people find partners is with services like this a lot, right? Especially in the Bay Area, it seems like it. And it's a, it's a very, it's a serious mathematical question. How am I going to make the most money? Well, hopefully the people I mean, surely the people that are designing these programs know about this, about matrix theory. And in fact, again, here's another fact about matroids that I'll mention very briefly, and I could say more about it. Matroids are precisely where the greedy algorithm works. So the greedy algorithm says, at each point, do the thing that seems the best, and keep doing that. Okay, that's not usually a very good idea to be so short-sighted, but matroids are precisely where this short-sighted greedy algorithm works. In other words, the algorithm that works here is saying, well, who is the woman that is paying the most money to be on the service? And let me make sure that she gets married first. Okay? And then who is the next one? And then and you continue like this. And this is the algorithm that works for this problem. And the reason it works is because this is a matrix. Okay? So there is a theorem that says that matrices are precisely the simplified complexes where the greedy algorithm works. Okay, so this was example 4, transversal matrix. And there's many, many, many more examples, okay? But I just wanted to give you a feeling of how one of the merits of this definition is that it's not a very restricted definition. And there's a lot of examples in several parts of mathematics where you have matrices, okay? And that means that if you can prove a theorem about matrices, then you're going to have immediately theorems about all of these things. Okay. And the beauty of matrix theory is that even though the axioms are very simple, actually matrices have enough structure that there's a lot of structure and a lot of theorems that you can apply to all of these settings. Okay, so in particular, and given this is a class in Hopf Algebras, you can expect that one of the things you can do with matrices is make a Hopf algebra out of them, and therefore you will have some Hopf algebra tools to study all of these questions. So let's do that. Instead of making this long list, let me just ask you to keep in mind this picture, which I think this one is the quickest to see. I think it's a little tricky to see if things are linearly, if they're algebraically independent, etc. But this is an easy picture, so just remember that's our running example. That matrix is going to be our running example. Maybe I'll write down the basis. So we're going to start doing some other construction of matrices. So let's say, by the way, let me also give you a word of warning about matrices, which is that matrices have many, many, many different points of view that are equivalent. And if you look up the definition of a matroid, you might find 10 different definitions, and they're all definitions of the same object, but it might not be clear ahead of time. So for example, I define a matroid to be a set E and a collection of independent sets. Okay, but now I'm going to change that. And it's to get you used to this kind of things. I'm just going to write it like this, where I'm just going to say these are the ground set. Okay, the elements that I can choose from, and I'm going to make a list of bases. Okay, And sometimes you'll see a definition of matroid that says a matroid is a set E and a collection of bases that satisfies these axioms. And the axioms are a little bit different from this because the axioms don't refer to independence. They're just a different set of axioms that work for bases. And just a word of warning that as you go into the literature on matroids, you'll see there's at least 5 very common definitions that people use that are different axiom systems, and then there's all these theorems that say that they're the same. I'm gonna try to stick with these as much as I can.
They call it
Right. So, yeah, so there's this word cryptomorphism, which is, I don't know, it's a very strange word, meaning that the theory of matroids through bases is equivalent to the theory of matroids through independent sets. It doesn't matter too much. I just want to give you a word of warning that especially if you're going to do the project on matroids, it might look different from what I'm doing today, but it is the same. Okay? If I have a matroid and I have an element, I'm going to make some constructions. Okay? So the deletion of E is the matroid. Sorry, the deletion is written M delete E of E in M. There's going to be a matroid which has ground set. It's just going to be the ground set you started with, but you delete the element E. And the basis I write the set like this. And this is just going to be the basis of my matroid that don't contain E. Okay, so B is a basis such that E is not an element of that basis. Okay? So maybe we can do an example. What is B backslash E? I'm going to look at all the bases here that don't contain the element E. So there are ABC, ABD, and ACD. Okay? So that's the deletion. Okay? Now the contraction is kind of the opposite thing. It looks at the bases that do contain E. Okay, this is called M slash E. E in M has ground set the same ground set, but the bases are going to be the ones that do contain E. Okay, so what are the bases that contain E? There are ABE and ACE. Okay. But one thing you'll notice about this is that because all of these bases contain E, E is just something that's getting in the way and not giving us any new information. Every single basis contains E, and so I can just delete E from all the bases, and I'm not adding or losing any information. Okay? And so that's what we do. We say these are the sets of the form B minus E, where B is a basis containing the element E. Okay? So these are just two constructions that I can make. So given a set of bases of a matroid, I mean, given the matroid and given this set of bases and given an element of the matroid, then I delete and I get this set of bases, and I contract and I get this set of bases. Okay? And as you might expect, the point is that these are also matroids. So proposition. These are matroids. Okay. Now, we had already seen these words of deletion and contraction in a different context, right? In the context of graph theory. So in graph theory, if you had a graph, what did it mean to delete? Which is meant to throw out that edge, right? So let's delete. What is the matroid of this graph? Well, let's look at what the bases are. So you cannot use F. You should always use A. And out of these three guys, you should choose any two of them. The bases are ABC, ABD, ACD, which are precisely these. Okay. I'm sorry? I said choose F. Sorry, I said don't. If you want to choose a basis, you don't choose F. You must choose A. And then out of these, you choose any two of them. Okay? And so these are the bases. Okay? And so one thing that should be cleared from, I mean, this is almost a proof of the fact that if you take a graph and you do the deletion in the graph, then the matroid of this guy is the deletion of the matroid of this guy. In other words, the notion of matroid deletion generalizes exactly the notion of graph deletion. On the class of graphs, they coincide. Okay. This is also going to be true for contraction. So remember what is contraction? Contraction is that you take the edge E and you just kind of squish it and identify the vertices. So what do I get when I contract the edge E? Well, A and F are untouched. But now these two vertices become the same vertex. And now that means that B and C are now edges that go from here to here. Right? And the edge D, now it's two vertices, two endpoints got identified. And so now it looks like this. Okay? And what are the bases of this guy? Well, you don't choose F, you don't choose D, you should certainly choose A, and out of B and C, you should choose one of them. And so you get this. And
that's why the E doesn't appear there. It's trivial in listing.
yeah, E disappeared in graph contraction, and here we also just get rid of it. And so that's the note that I want to make, that these operations directly generalize deletion and contraction in graphs. Okay. Now, that means you have notions of deletion and contraction for all of these other kinds of things that I did. And so, for example, given a set of vectors, what do you think deletion and contraction are? So projection is one of them, and deletion is kind of deletion still. Okay? So imagine you have a configuration of vectors. So what is the deletion of a vector is you just forget that that vector exists. Okay? That's a geometric operation of just throwing a vector away. And contraction is going to be exactly projection. Projection into where? Well, you see, what you want is you have your collection of vectors and you have your vector E that you want to contract. And so what you do is that you project onto the plane normal to that guy. And if you project everything onto that one, then the vector E kind of collapses and disappears. And then the bases that you get are precisely the bases of the contraction. Okay? And so deletion and contraction also have a geometric meaning. That's very important. Okay. Now, just like with graphs, properties. Let me say some obvious properties. One obvious property is that if you have a matroid and you start deleting if you delete A and then B, that's the same thing as if you delete B and then A. Right? That's pretty obvious, right? And that means that, okay, let me just write some things down. If you take a matroid and you contract A and you contract B, that is the same thing as if you first contract B and then you contract A. Again, that's pretty obvious. You're going to get the bases that contain A and B. Okay. What's maybe a little bit less, well, I don't know. This is also easy, actually. It's not maybe equally obvious. If you delete A and you contract B, then you're picking out the bases that do not contain A and do contain B. It doesn't matter what order you do it. Okay. And this allows me to make some definitions that if A is, let's say, A1 up to AK, then the deletion, then I can delete the whole set. Okay, the deletion of the whole set is just deleting the elements one at a time. And the contraction of the whole set is contracting the elements one at a time. And I can also define the restriction to that set. What should that be? It's actually going to be just as in graph theory. So if you want to restrict to, if you have, you have your whole set A, E, and you want to restrict to the subset A, that's equivalent to just deleting everything that you don't want to pay attention to. So it's taking M and deleting the elements you don't care about. Okay. Yeah. And so here I've defined a more general deletion and contraction. And also, I did this for graphs and I'm going to do it again. If A is a subset of B, is a subset of E, then I can define the notion of what is the matroid, the kind of interval matroid from A to B. And what is this? Well, let me kind of draw a schematic picture. So here's E, here's B, here's A. And so what you want to do is basically look at the things between A and B. And so what you want to do is just restrict your attention to B and squish A, contract A. And so I can do this in a couple of ways. First, I could contract A and then delete the elements in E minus B, or I could do it in the other order. I could delete the elements in E minus B and then squish A, contract A. Okay. And this is the notion of, you have a matroid on the whole set. And now what you're going to do is just, look at the matrix between A and B. Okay, so I'm just repeating what I said earlier. So basically, you're looking at the things that contain A and are contained in B. And so then what you're doing is you're contracting the stuff in A to make sure that you contain A, and you're restricting to B, which is the same as deleting E minus B. Okay, so this is some kind of notion of restricting M to an integer, which we know is the kind of thing that is very useful for Hopf constructions. Okay. So let me ask you now. Okay, remember what we're trying to do here is build a Hopf algebra. Okay. So what do we have out of the ingredients for a Hopf algebra here? Can you think of how to define, I don't know, part of the Hopf algebra? So what should the coproduct be?
Deletion of one, coordinate, and contraction of the other.
So remember that we did this for graphs, right? We had this Hopf algebra of graphs. Now remember we've seen two different Hopf algebras of graphs. But in one of them, you did this thing where you restricted to the first in the first coordinate you restricted, in the second coordinate you contracted. Okay? And given that we have notions of restriction and contraction that directly generalize those of graphs, then you would hope that that's a suitable coproduct. Okay? And in fact it is. Okay, so I'll write it down in a minute. So this means that we do have a coproduct on matroids. What about a product? Do we know how to multiply matroids? So we haven't written it down, so we should think of what should we do? And again, thinking that, I mean, one of the nice things about matroids is that because you have all these different examples, you have graphs, you have linear algebra, that means that you can take any ideas that you know from any of these things and try to lift them to matroids. Okay? And so you said disjoint union, and maybe you're thinking that the thing is that for graphs, yeah, so Brian is doing the same thing over here, where he's thinking, okay, how do we multiply two graphs? Well, you just kind of put, you had them, each graph in one hand, and you just kind of put them next to each other. That's the multiplication. It's called the direct sum of graphs. And so given that that works for graphs, and given that graphs are a sub-example of this, then probably we should try to do something similar here and define the direct sum of two matrices. Okay. So what should the direct sum of two matrices be? And again, the nice thing about this is that we know what it is for graphs. And so the definition that we make is kind of hopefully dictated by that. Okay, so say that again, Brian? So let me start with two matroids, M and M prime. And I want to define the direct sum. The direct sum M direct sum M prime has ground set. Brian is suggesting that I should make it the disjoint union of my two ground sets. And now we need to define the basis, and again we should think about how this works out for graphs and then write it down in this language. Okay? So what are the bases of the disjoint union of two graphs?
Basis for E times the basis for E prime.
So remember, a basis is a maximal set with no cycles. Now you have two graphs and they're sitting next to each other and they're not interacting. So if you want to have a graph with no cycles, you just do something on this side, something on this side. And if you want it to be maximal, you make sure that it's maximal here and maximal here. So the bases are just going to be take a basis of the first guy, a basis of the second guy, and take their union. And so that's what we're going to do. B union B prime such that B is a basis of the first matroid and B prime is a basis of the second matroid. Yeah, disjoint union. Okay. And presumably this should be the product of our Hopf algebra that we're trying to build. And the good news is, which maybe you imagined already, is that this all works out. So theorem. And this is a theorem that was anticipated by Rhoda, and I think really first written down completely by Schmidt. There is a Hopf algebra Let me write it down like this. The product of matroids given by disjoint union and the coproduct given by, again, you sum over the subsets of the ground set, just like we did with graphs. You restrict in the first coordinate, and tensor, you contract in the second coordinate. Okay? This product and this coproduct give a Hopf algebra of matrix. And I should say that, to make this fully precise, I need to say more things. I need to say what the unit is. I need to say what the co-unit is, etc. But you've seen this enough times that I think I'll spare you the details, and you will know how to fill them. And if you're not sure how to fill them, then look at what were for graphs, and then do the same thing here. Okay. So we have a Hopf algebra of matroids. Now, let me ask you something. If we have a Hopf algebra of matroids, does that mean that we have a Hopf algebra of graphical matroids, a Hopf algebra of linear matroids, a Hopf algebra of transversal matroids, a Hopf algebra of, what was the other one I said? Algebraic matroids? Are those things true? For example, can I say that the Hopf algebra of graphs lives inside the Hopf algebra of matroids? Or rather, does this one contain a copy of the Hopf algebra of graphs? Sure, right? Just look at the subalgebra of this generated by graphical matroids. Okay. Well, the product on two graphical matroids coincides with the product of the joint union of graphs, which was the product in the Hopf algebra of graphs. This operation is exactly the same as we have for graphs, and therefore, if you restrict the subalgebra of graphical matroids, it is isomorphic to the one graphs. Actually, that raises an interesting question, actually. Okay, so I didn't plan to get into these subtleties, but since I got myself into this, then now I have to. But I think it's interesting. So let's make some comments about this. Is the Hopf algebra of graphs a sub-Hopf algebra of the Hopf algebra of matroids? So the answer is kind of, but not really. Let me explain to you why. Like we said, if you restrict to graphical matroids, then the operations work in the same way. Okay. Now the problem though is this: can you have two different? We need a. Okay, so let's say it like this: we have a map from let's say the Hopf algebra of graphs to the Hopf algebra of matrices. I just defined it. From a graph, go to the graphical matrix. And this is a Hopf algebra map because we just discussed how it preserves all the operations. Is this an isomorphism? That's the issue. Oh no, but actually, we know it's not an isomorphism because it's not surjective. We talked about how there's matrices that don't come from this. Okay, it's definitely not an isomorphism. It's not surjective, but I don't need it to be an isomorphism because I just want to know if this is a subalgebra. In other words, I need to know if this lives inside here. So what property would I need this map to satisfy if I want this to be a subalgebra of this?
Would it be enough for it to be a homomorphism?
It is a homomorphism, and it's not enough because it needs to be injective, right? Because, phi of h of g is a subalgebra of h of m by definition, because it's a homomorphism. But the question is phi of h of g a copy of h of g? And for that, I need phi to be injective. Yeah?
Is your question whether there are more than one matroid which is represented as a graph?
That's right. So is phi injective? You see, this is one reason that I want to keep going down this line of thought is that I want you to notice that by trying to answer a completely algebraic question, you end up with a completely combinatorial question that you need to answer. What does it mean? What does this question mean? Well, Brian translated it for us into the theory, into the language of only graphs and matrices. The question is, can you have two different graphs that have the same matroid? Can you think of two graphs that have the same matroid, but they're different?
When you were drawing one earlier, could you just include one more loop? Say you had F, you don't want to include F, you just go ahead and draw another loop.
I can always put loops. Well, no. Okay, so here's one graph that has a certain matroid. So Steven is suggesting that I could add another loop. Does that change the matroid? It doesn't change the set of independencies, but it changes the gram set. The matroid is a pair E and I. If I add an edge, I don't change. If I add a loop, I don't change I, but I do change E. And so it's not really the same matroid.
What I was thinking about the other, we could deal with that by just modding out by loops in our graphs.
Okay, so let me make a couple of comments. So one thing that I can do a little bit differently is that instead I can erase this loop here and put it somewhere else. The matroid doesn't see loops, right? So if the matroid doesn't see loops, that means that I can put loops in different places and the matroid is not going to know. And so this is one way in which the answer is no. Yeah?
Do we have some kind of congruence? Can we call these congruent?
So can I mod out by loops? Is that going to work? Okay, so can I, in a less trivial way, change this graph and not change the matroid? I claim that I can, because I can take this edge and I can move it over here. And the matroid doesn't know, because the matroid only knew that it was supposed to throw in this set everywhere. Okay? And if it's here, or if it's here, that doesn't change the matroid at all. Okay? And these are really two graphs that, in graphland, we want to call them different, and the matrices are not different. Okay? And so that's why the answer is kind of, but not really. The next question you should ask is, okay, can we tell whether two graphs have the same matroid or not? and so that I can mod out by that, right? So question, can I know when do two graphs have the same matroid?
What if you consider instead the Euler characteristic for
Yeah, I'm not sure how that would help. When do two graphs have the same matroid? Well, actually, that's a very natural question that if we can answer, we should answer, and it is answered. So this is given by Whitney's two isomorphism theorem, and it's a little bit tricky actually. Two isomorphism theorem, and this theorem says that two graphs have the same matroid if and only if they're two isomorphic. And two isomorphic is a word that he had to invent. And basically what he does is that he explains that if two graphs have the same matroid, then I can obtain one from the other one by doing some kind of local operations. They're not trivial operations, but so anyway, so this is how a purely algebraic question leads us to some interesting pure combinatorics. Okay, let me ask a different question. Is there some sort of a Hopf algebra of transversal matroids? Well, let's see. So we could restrict to transversal matrix here. So here's the product, here's the coproduct. Is that going to work or not? It's a little bit tricky. And the reason is that I could feed a transversal matrix into this formula. Or, I mean, let's do it here. I can feed two transversal matrices into this formula. Is this going to be a transversal matrix? What do you think? I have some kind of M is some kind of matching problem. M prime is some kind of matching problem. What is the product? Well, this seems okay to me actually, because probably it's just kind of matching here and matching here. And that works out. You can see that if M and M prime are transversal matrices, then this is a transversal matrix. What about here? Feed is a transversal matrix. If we want this to be a sub-Hopf algebra, it needs to be closed under the operations, right? And so these guys, we will want them to be transversal matrices. So is it true that the restriction of a transversal matroid is transversal? Is it true that the contraction of a transversal matroid is transversal? Is there a match corresponding to only restricting to a certain set? It means, can you invent a new matching problem like that? And it turns out the answer is no, actually. So it turns out that it's no, and it's a non-trivial thing to answer, but it turns out that if M is transversal, then the contraction is always transversal, and the restriction is not necessarily transversal. Okay? And then you say, okay, well, that sucks, you know. I wanted a transversal matroid Hopf algebra, but this didn't work. So then what should I do? You can say, well, you know, then what are the, you know, maybe let's enlarge the class. Okay, if I want transversal matrices in my Hopf algebra, then I need to include restrictions of transversal matrices as part of the Hopf algebra if I want this to work. So I need to enlarge the class and go outside of transversal matrices to transversal restriction something. And then I say, okay, if my matrices are of the form transversal restricted to something, is that family closed under the operations? And it turns out that it is. And it turns out that transversal restricted something is a family called gamoids. Okay. And so I think somebody's going to do their project about gamoids, and so I thought this would be useful to mention. So gamoids are the smallest family that you can put here so that you can make a Hopf algebra of transversal matrix. If you want transversal matrix to live here in your sub-Hopf algebra, then you're forced to put all the gamoids, which are a wider class of matroids coming from some kind of routing problems. It's a nice family. Okay? But basically, this says that if so the answer to this is no. No, but you can enlarge to a bigger class. Gamoids, which are closed under deletion and contraction. Okay? And the point is that you can always make a sub-Hopf algebra of matroids as long as it is closed under these operations. Okay? And so let me say that any family closed under disjoint union, restriction, and contraction gives you a Hopf algebra. Any family of matroids closed under direct sum, restriction, and contraction gives you a sub-Hopf algebra. And you can ask, okay, well, what is that Hopf algebra? And one of the projects that I wrote down is that actually I've never seen anybody describe what this Hopf algebra looks like. I mean, there is a Hopf algebra of gamoids. Can you say more about it than the fact that it exists? And so hopefully we'll have an answer by the end of the semester, right? Anyway, so yeah, question? Maybe I'll draw a chart. Here's matroids. Here's linear matroids. Actually, yeah, linear matroids. Remember, linear is a tiny class, but I just make it big because I need to fit more balls in here. So I guess then I have gamoids, which contain transversals, and then graphical matroids are kind of like this. So graphical